Let us see an example on pole 0 plot. Okay, the question is determine the pole 0 plot for the signal x of n is equal to a to the power of n u of n, where a is greater than 0. So now we have to not only identify the poles and zeros here, but also we have to plot them, and as an addition what we do is we'll try to understand where does the ROC lie. So this will help us in clearly understanding the significance of poles or zeros. Okay, let us start the solution. Okay, let us find x of z for this. Okay, x of z will be from this, as you have done earlier, this will be equal to, okay, from this I can write this as, okay, this already we have done earlier, where we have calculated the z transform from a given signal. Now our aim is now to look at this equation and find out how many poles are there and how many zeros are there. How many number of zeros are there? There is number of zeros are 1 and number of poles are 1. Okay, so where does the 0 lie? The 0 lies at z is equal to 0 and the pole lies at z is equal to a. So let us plot this. Okay, let us plot this on the diagram. So we have this is my real axis and this is my imaginary axis. Okay, as we have seen earlier, zeros are represented by a 0 like this and poles are represented by a cross like this. Now let us first see 0. Where is the 0 lying? The 0 is lying at this origin. Okay, so I will put a 0 here. This is at the origin. Whereas where is the pole? The pole is lying at A. That is, let us say A is here. So we mark it by a cross. So this is A. Okay, now you have a 0 and you have pole. Now how do I find out the ROC for this? The ROC is, if you look at this, ROC does not include the pole A. Why? Because the definition of pole itself says that the pole will make x of z value diverge. So ROC must not contain the pole. If it contains a pole, then it diverges, region of convergence. That means there is no convergence. So where will that lie? It will lie beyond this circle A. Okay, if I take this circle like this, then ROC will be this region here. And as you see here, the ROC does not contain the pole. Otherwise, it is not an ROC at all. So this is how we calculate the zeros and poles in this equation. Let us see the second example. The second example is determine the pole 0 plot for the signal given x of n is equal to a to the power of n, which lies between 0 and m minus 1 and 0 elsewhere. Let us see this problem. Okay, let's look at this equation. What is the solution? X of z. Okay, from this is directly, I am directly writing az to the power of minus 1 whole to the power of m by 1 minus az to the power of minus 1. Okay, so this will be equal to z to the power of m minus a to the power of m by z to the power of m minus 1 z minus a. So this is the equation for this. Let us now determine the pole 0 plot for this given equation. So we have x of n is equal to a to the power of n, where a to the power of n, for these values n lies between 0 and m minus 1 and 0 elsewhere. So if I take this a transform for this, the transform is given by this equation and is equal to zm is equal to minus a to the power of m z minus 1 into z minus a. Okay, now if you look at this, at a greater than 0, okay, so zm is equal to a to the power of m. So how many roots we have here? We have m roots. Okay, we have m roots there. And also we have a cancellation. You know, we have a 0 at A, okay, which cancels the pole at A. So this is what is in from this you can look at this. Now let us take a certain value of m. Let us say m is equal to 8, because m is, you know, we do not know the number. For m is equal to 8, let us draw the figure. How does it look like? Okay, for m. So for m is equal to 8, I have how many zeros? I have, from this equation, I have 8 zeros, and I have 8 poles which are at the 0. So that's how it looks like. Okay, so let us just draw this graph. Okay, here this is where 8 poles exist, and we have m number of zeros which are existing at e to the power of j2 pi k n by 4. So if you substitute the where k is equal to 0 to m again, so you have 8 zeros for this. So where do they exist? E to the power of j2 pi k n by 4. So there will be 1 0 here, 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 1 here and 1 here. 1, 2, 3, 4, 5, 6, 7, 8. So you have all these zeros like this. So this is the pole 0 plot for a given equation which is having m roots. So m roots means I have taken m is equal to 8. So you have 8 zeros which are located at these positions, isn't it? R e to the power of j2 pi n k by 4. So this is the position at which the zeros exist. So we have 8 zeros which are existing here, and also we have 8 poles because of the fact this, and this is where they are existing, and one pole is cancelled by the z is equal to a 0, where you have both a 0 which is cancelling a pole in that case. So let's talk about the significance of pole location and how do they influence the time domain signals. How do they influence? I repeat, how do they influence the time domain behavior of a causal signal? That means we try to understand the significance of the pole position. The pole position tells us how will your signal behave in time domain. So let us look at that now clearly. So let us start with the first point. The point says the characteristic behavior of the causal signals depends on whether the poles of the transform are contained in the region z is equal to less than 1, or in the region z is greater than 1, or on the circle z is equal to 1. Okay, of course, z is equal to 1, that means radius is equal to 1, it is called as a unit circle. That means here we are trying to see 3 cases of the location of pole. But let us take a circle, let us say it is unit circle. Okay, this is a unit circle. We are talking about 3 cases. The case 1 where the pole lies, if suppose let us say this is 1, that is this is a, okay, I should not put like this, I should like this. So let us say this is the radius is 1, that's a unit circle. If the pole lies somewhere inside, then there is one type of behavior of your system, that is one case. Then the case 2 where this, here you can write it like this is less than that, because we are talking about a unit circle, the pole will lie inside the circle now. Then there is another case where I can put my z is equal to 1, that means exactly I can put a pole here. The pole here or pole can also be here. When I am talking about the RHS, it is equally applicable to LHS also. We will see how they do differ a little later. But now this is the case 3. Case 2. Now let us talk about case 3. Case 3 is when the pole lies outside the unit circle. That means I have a pole somewhere here. Then these are 3 cases which we have to study, and we have to take into consideration the time domain description so that we can understand how the system is going to behave in all the 3 cases. The case 1 where z is less than 1, case 2 where z is equal to 1, and case 3 where z is less than 1. So all these cases we have to give a detailed understanding, or we have to give a detailed look into this so that we can understand the time domain behavior of your signal, particularly for causal signals. Now let us take up those cases. There's one other point, important point which we have to think about here is, if a signal is real and its z transform has only one pole, then that pole must be real. Then the such signal is only a real exponential. So if we talk about the first example which we have seen today, x of n is equal to a to the power of a u of n. it is having an ROC for Z greater than or equal to A. Here if you see, there is a 0 at Z1 is equal to 0. We are calling it Z1, there is no other zeros, so there is only one 0 that is present and which is existing at Z1 is equal to 0. And the number of poles present in the example which you have seen, P1 is only one pole, that is equal to A on the real axis. Okay. Let us describe all these things, let us understand them in detail now. The figure below, the figure that is being shown now, discusses about different cases which we have seen earlier. Case 1, where the pole lies inside the circle. Case 2, where the pole lies on the circle, and the case 3, where the pole lies outside the circle. Here we are assuming that the circle is unit circle. So the pole which is less than 1 lies inside the circle, is equal to 1 lies on the circle, and a pole which outside the circle, that means it will be greater than value of 1. Let us look at these figures below. So first, looking at the first figure. The first figure is the case 1 here. You see a Z plane, and you see here clearly the pole is lying inside the circle. Here we have, for convenience sake, we have assumed the circle as a unit circle. Okay. So if you see here, the pole is at a value which is less than the 1. So it is lying inside the circle. So how will be the time domain behavior? If you see here, the x of n is exponentially decreasing. That is, it is a decreasing function. Then let us look at the case 2, where the pole is lying on the plane, Z plane, that is, it is equal to 1. Then what will be the behavior of time domain behavior? If you see the second figure here, the time domain x of n is constant. It is maintaining a constant value, it is not shifting. Now when you look at the third figure, what is the third figure says? If you see the figure clearly, here the pole is lying outside the circle. And you see x of n is growing. So these three are very important aspects. So significantly, if you look at the figure on the left hand side of your figure, here you see the pole is lying on the positive axis. We are not talking about a pole which is lying on the negative axis. So three cases. The case 1, where the pole is inside the circle, you see x of n which is exponentially decreasing, or it's a decaying function. Then the pole is on the circle, unit circle, then it's the x of n is constant, is not varying with time. And third case, where the pole is lying outside the circle, you see that there is an exponential growth in the time behavior. This is in the case of a signal which is on the positive x-axis. Now on the other side of the figure, you see here a pole. Of course, case 1 is satisfied. Case 1, we are talking about a pole which is less than 1. It is lying inside the circle. But where is the pole now lying? The pole is lying on the other side of the axis. If you look at the time domain behavior, there seems to be an oscillatory action, x of n. So there are some positive values and also negative values. So as you see here, it's again decaying, but there is a negative value, positive value, negative value, positive value, negative value, positive value. In the case of the pole lying on the circle, you see that in fact there is no change in the value of the signal in time domain, but in fact there is a change in sign. Okay, change in sign is happening. See here, the signal is not decaying nor growing, but it is remaining constant, but it is having both negative values and positive values. Probably you can call this as an oscillating value. But the important point to be noted here is there are some negative values which you are getting in the output time domain representation. When you finally look at the pole which is lying outside the circle, you see same thing here, but it is growing. So in fact, you can establish a relationship between a pole which is lying on the positive axis and which is a pole lying on the negative axis with a negative plane. So if you understand this behavior, then understanding the time domain behavior of a causal signal with respect to pole is very easy. Now let us summarize this, whatever I have spoken about. So pole inside the unit circle, the signal is decaying, of course. Pole outside the unit circle, the signal is growing. And pole on the circle, the signal is fixed. And whenever I have a negative pole, a signal that alternates in sign. So you have a positive pole, there is a certain behavior, and for a negative pole, there is a alternative in sign. So there seems to be an oscillation between the positive value and the negative value. Let us move on. Causal signals with poles outside the unit circle become unbounded, cause overflow of the digital systems, and must be avoided. So talk about any causal system, then avoid having a pole outside the unit circle. If it is present, it results in what is called as unbounded, that is, the system is becoming unstable. It causes overflow in digital systems and therefore must be strictly avoided in the case of a digital system design. Then if you look at a causal real signal with a double real pole as this form, what is a double real pole? X of n is equal to n of n into a to the power of n u of n. So this creates a double pole, and let us look at different cases of double pole in this figure. So first figure you see here, we have two poles which are lying inside the circle. Okay, and then in the second case where you see the pole, two poles lying on the circle, and similarly you have a pole, double pole lying outside the circle. Similarly, you have a double pole which is negative lying inside the circle, then you have a double pole lying on the circle on the negative side, negative pole, and then again you have two negative poles which are lying on the circle outside the circle. All these three cases. If you look at these figures, it is very clear how the behavior is happening. Okay, if you look at this, a double real pole on the unit circle results in an unbounded signal. A double real pole on the unit circle results in an unbounded signal. So let us again look at this figure in figure for us to understand this better. See the case here, a double pole lying inside the circle. There is an exponential decay that is happening. Okay, there seems to be a oscillation type of thing that is happening. In second case, you can also see where double poles are lying on the circle, and in third case, you see the pole lying outside the circle. So this is how the behavior can be established. Now let's talk about a pair of complex conjugate poles. What is a pair of complex conjugate poles? Result in exponentially weighted sinusoidal signal. Okay, so you have a sinusoidal signal which is getting multiplied by a exponential signal. That is, there is a weighing factor which is exponential in nature for the case of a complex conjugate poles. The distance r of the poles from the origin determines the envelope of the sinusoidal signal and their angle with the real positive axis and its relative frequency. So what is this we are talking about? The distance r of the poles from the origin. So they determine the envelope of the sinusoidal signal and their angle with real positive axis, its relative frequency. So these two are going to help us in analysis of a complex conjugate poles. And look at the amplitude of the signal is growing if r is greater than 1. If r is equal to 1, it is a constant sinusoidal signal, and r is less than 1, it is a decaying sinusoidal signal. So you have a sinusoidal signal which is exponentially growing, or it is remaining constant, or it is exponentially decaying. These are the three cases in the case of a complex conjugate pole. You see here in this figure, the first case, you see the pole where r is less than 1 in this case here. And then the second case you talk about r is equal to 1, other case where r is greater than 1. You see the weighing factor. The weighing factor, as you see here, is on the right hand side, is determining. In the first case there is a exponential decay, that is, weighing factor is getting reduced, which is exponentially decreasing the signal. The second case it is constant, as is obvious, and the third case there is an exponential growth. So r is telling how does your sinusoidal signal behave, weighing factor. Okay. Now let's look at multiple poles on the unit circle. If there are more than one pole which is lying on a unit circle, it should be treated with a very great care, because causal signals with simple real poles or simple complex conjugate pairs of poles which are inside the unit circle are always bounded in amplitude. This is a very important point which you all should remember. What is the point? Causal signals with simple real poles or simple complex conjugate pairs of poles which are inside the unit circle are always bounded in amplitude. Okay, we also talk about a signal near or almost equal to. So third point is a signal with a pole near the origin decays more rapidly than the one associated with a pole near or inside the unit circle. This is a very important point. So talk about a pole which is near the origin, and you talk about a pole which is near the unit circle. So let us see that. If you look at a pole here, the first pole, let us say a pole is very near the origin and another pole is very near the unit circle. And remember, we are talking, the condition here is both are in the unit circle. So what will happen in the first case? Okay, if the first case, if you look at the slide here, it says the pole near the origin decays more rapidly. So this pole is decaying your signal more rapidly. That means the fall of your signal or the decaying of signal is rapid in the case of a pole which is existing very near to the origin. Now you talk about a pole which is away but nearer to the unit circle and which is inside the unit circle, the decay will be a little slow. That means here the decay is faster. Let us, if I look at this, the decay will be very fast like this. In this case, the decay will be slow like this. So this is what is the location of poles is going to tell us how the design has to be adjusted. The time behavior of the signal depends strongly on the location of its poles relative to the unit circle. As we have seen in the earlier figures, we have studied the different cases of the location of pole versus the time behavior of the signal. It's very clear there is a strong relationship between the pole location and its relative position in the time domain. Zeros also affect the behavior of a signal but not strongly as poles. You have got the dot why we are talking about only poles, but zeros also have some effect on the behavior of the signal, but the effect of poles is more compared to the effect of zeros. For example, we are given here, in the case of sinusoidal signals, the presence and location of zeros affects only their phase. That means only the phase of a sinusoidal signal is affected with respect to the change in the location of a zero. Okay, an important note here, if a pole of a system is outside the unit circle, the impulse response system becomes unbounded and consequently the system is unstable. So again, even impulse response also is becoming unbounded and consequently what is happening? The system is becoming unstable. So any pole which is present outside the unit circle, the system is not bounded. That is, it is resulting in an unstable system. Let us talk about the behavior of a transient and steady state responses of a system. What is a transient response and what is a steady state response of a system? Okay, the first point, the response of a system for a given input can be separated into two components, a natural response and a forced response. The response of a system, the two components, one is a natural response . Natural response, and the second one is a forced response. Now let us look at the natural response first. Natural response, if you look at this equation here, the equation is y(n)r of n is equal to sigma summation k is equal to 1 to n ak pk to the power of n and u of n. Let me write this on the board. For this natural response y, okay, we are using nr here to indicate natural response of a function n. This is equal to summation okay. So this is the equation for a natural response. As we have been using since some time, that y is used as a response. So here nr we are adding to indicate that it's a natural response. This will be equal to a summation k is equal to 1 to n ak, which is some multiplying constant, and pk to the power of n u of n. So this is the natural response of a system. So let us see what is this, where p of k is k is equal to 1 to n are the poles of the system, and the factor ak are scale factors that depend on the initial conditions and on the characteristics of the input sequence. So here p denotes the poles present, where k can be equal to 1, 2 to the power n and again, and ak is a scale factor that depends on initial conditions and characteristic of the input sequence. So this is a scaling factor. This is the scaling factor, and these are the poles, okay, where k is equal to 1, 2, so on. So this is how we get the natural response of a system. If mod pk is less than 1 for all k, thenynr of n decays to 0 as n approaches infinity. If p of k is equal to less than 1 for all values of k, then ynr decays to 0 as n approach to infinity. That means, what does it indicate? P of k less than 1 means what? The poles are lying inside the circle. So the signal has to decay. When it will decay? As n approaches infinity, it will go to 0. Otherwise, it will be a decaying function. Okay, in such case, we refer to the natural response system as a transient response. The rate of which ynr of n decays towards 0 depends on the magnitude of the pole positions. So these are some important points. Okay, so what are the points here? P of k, if this is less than 1, then the signal decays. Okay, and we refer this type of response is called a transient response because this will decay to 0 when n is tending towards infinity. So that's a decay, and the amount of decay depends on the magnitude of the poles. So the poles magnitude also helps us in identifying by how much factor or the decay is happening. If all the poles have small magnitude, the decay is very rapid. If one or poles are located near the unit circle, the corresponding terms in ynr of n will decay slowly towards 0, and the transient will persist for a relatively very long time. These are again some of the few points which you have to understand. The first point is, if all the poles have small magnitude, the decay is very rapid. And if our one or poles are located near the unit circle, the corresponding terms in ynr of n will decay slowly towards 0, and the transient will persist for a relatively long time. Okay, so the pole location nearer to the circle, not outside but not near 0 also, they are nearer to the circle, then what happens? The transient is slow. That means the transient is persisting, okay, for a long time. It is not a transient that is decaying or becoming 0 very fast. The transient will persist. For that, what is that we have to see? We have to see and ensure that the poles are nearer to the unit circle. Okay, and if you want the decay to be fast, then the magnitude of the poles, if they are small, then the decay will be very rapid. Now let us look at the other one, that is the forced response. So what's the forced response? The system has this form. The forced response system has this form. So we are indicating this by LR, that is given by summation k is equal to 1 to L we will see the forced response form. It is given by LR of n, and it is given by summation of k is equal to 1 to capital L, capital Q of k, small q of k to the power of n, u of n. Again here, this represents the number of poles here present, okay, on the forcing function. Earlier it was not a forcing function because this is a forced response, the input must be a forcing function. So this gives the poles of that unit function, okay, of that forcing function. So here you see qk, where k is from 1 to L, are the poles in the forcing function, and capital Qk is a scaling factor that depends on the input sequence and on the characteristics of the system. So these are poles, again as we have seen earlier, these are the poles, but now these are the poles of the forcing function, and this is the scaling factor, okay, and depends on so many things, that includes the characteristics of the system also. If all the poles fall inside the unit circle, YLR of n will decay towards 0 as n approaches infinity. And this is same as in the case of a natural response. The natural response also we said the same. If they fall inside the unit circle, then the decay will be slow and it will fall to 0 when the n function becomes infinity. This in fact same as that in the case of a natural response. Why? Because the input signal is again a transient. That's the reason, because the input signal is transient, the forced response also a part of it is similar to the case of a natural response. Now, when the input signal is sinusoidal, then what happens? The poles fall on the unit circle. When the input causal signal is sinusoidal, then the forced response is also a sinusoid that persists for all n greater than or equal to 0, because now the pole is lying on the circle. So the signal will, sinusoidal signal will persist for all values of n greater than or equal to 0. So the signal is not decaying, that is very important. So, and if you observe the type of response that is coming out in the first response, that is here, that is the response is same, which is persisting for all values of n greater than or equal to 0. That is why this type of response is also called famously as the steady state response, because neither the signal is decaying as we have seen in the case of the other response here. So it's called also called as a steady state response of the system. So what should I do? For a system to sustain a steady state, output for n greater than or equal to 0, the input signal must persist for all values of n greater than or equal to 0. Now I want the steady state output for all values of n greater than or equal to 0. We expect that the input signal is also persisting for all values of n greater than or equal to 0. Now let us see an example. Example here. So what does the example say? We are supposed to determine the transient and steady state response of the system characterized by the difference equation y of n is equal to 0.5 y of n minus 1 plus x of n. So let us see what is that. So okay, now this is what is the difference equation given. We have to determine the transient response and the steady state response of this type of system. The system's difference equation is given clearly here. So we'll see what is the input given. Again, input is also given. If you see this slide here, the input talks about signal which is sinusoidal. In fact, x of n is equal to 10 cos pi n by 4 u of n. And also the other condition given is the system is generally at rest, that is, it is a system which is relaxed. So these are the conditions. So a difference equation is given, you have a type of input given, and also the initial conditions are given. Now we have to calculate the transient and steady state response of the system. So let us see how it is done. Now as we are trying to calculate the response, system functions, other things are calculated with our knowledge which is known. So if you see on the slide, h of z is equal to 1 by 1 minus 0.5 z to the power of minus 1. So from this very clear that there is a pole that is existing at z is equal to 0.5. So z is existing at 0.5. If it is unit circle, it is lying inside the unit circle. And then the z transform also we are calculating here. So what is the z transform x of z? X of z is given by 10 onto 1 minus 1 by root 2 z to the power of minus 1 by 1 minus root 2 z to the power of minus 1 plus z to the power of minus 2. What is the response y of z? Y of z is equal to h of z multiplied by x of z. So it is a system, isn't it? So you know. So if I take this as z transform, this is having a transfer function here, and this is my input. We are talking it in terms of x of z. Then I am taking this as y of z, which is a response. Then from this you know very well that y of z is equal to h of z and multiplied by x of z. So this is what we have to do now. Okay, now we know what is h of z. X of z is already given to you. So multiplying these two and taking into consideration the initial conditions, I will get my value for y of z. So let us do this here. So we are multiplying here, y of z is equal to h of z, x of z. So we know the value of h of z, we know the value of x of z, and we have got a certain value. After certain manipulations we got y of z is equal to 6.3 by 1 minus 0.5 z to the power of minus 1 plus 6.8 e to the power of minus j 28.7 by 1 minus e to the power of j pi by 4 z minus 1 plus 6.78 e to the power of j 28.7 by 1 minus e to the power of minus j pi by 4 z minus 1. This is my output response. Now from this response we have to find out what is a natural response, what is a steady state response. If you look at this natural state response is given by y and r of n is equal to the first term, that is 6.3 multiplied by 0.5 to the power of n u of n. This is the natural response. So if you look at the figure, it is a natural response which we are talking about. Then comes your forced or steady state response. So what is the forced response, the steady state response? If you look at this, we spoke about a weighing factor is present in the case of a forced response. So if you look at the forced response given by YLR of n, that is equal to 6.78 to the power of minus j 28.7 e to the power of j pi n by 4 plus 6.78 e to the power of j 28.7 multiplied by e to the power of minus j pi n by 4, all this u of n. So if you add this, you will get a value which is equal to 13.56. It is a cosine function, cos pi by 4n minus 28.7 u of n. So it is weighed by a factor 13.56. Now the steady state response, what is the steady state response? It persists for all values of n greater than or equal to, just as the input is persisting for values n greater than or equal to 0. So this is the steady state response of the given system. Now let us look at causality and stability with respect to the poles and zeros. Okay, a causal linear time invariant system is one whose unit sample response h of n satisfies the condition h of n is equal to 0 for n less than 0. The ROC of Z transform of a causal sequence is the exterior of a circle. The ROC, as we have seen earlier in the first example today, we have seen that the ROC is exterior to the circle. So that's what we are talking about here also. Okay, I call a LTI system causal if and only if the ROC of system function is exterior of a circle of radius r less than infinity, including the point z is equal to infinity. So the system, LTI system is causal only if this ROC of the system is exterior of a circle of radius r less than infinity, including the point z is equal to infinity. Now let us look at a causal linear time invariant system is basic BIBO, basically BIBO stable if and only if all the poles of h of z are inside the unit circle. So a linear times invariant system must have all the poles lying inside the unit circle only and is causal only then. So all the poles must be present inside the unit circle. Once this is done, then only we can assure that the system is basically BIBO, that is bounded input, bounded output, stability is present. Now let us look at a concept called as pole-zero cancellations. So how can a pole cancel a zero cancellation? How can a pole cancel a zero and what are the effects of it? We have made a passing reference to how a pole and a zero can be cancelled in our earlier example. Now let us look at this. When a Z transform has a pole that is at the same location as a zero, the pole is cancelled by the zero. In our earlier example also, we have a particular case where the pole and the zero are existing at the same place. So when they do exist at the same place, what happens? The zero cancels the pole. Now what happens? Consequently, the term containing the pole in the inverse Z transform vanishes. So we don't have a pole and the term associated with the inverse Z transform, that also is vanishing. Now we can talk about how a pole zero cancellation can occur. Pole zero cancellations can occur either in case 1, the system function itself, or case 2, in the product of the system function with the Z transform of the input signal. So system itself can enable the cancellations of zero poles, as one case, or second case, I can have a system function product multiplied with a Z transform of the signal, then also I can get a case where these two can be cancelled. Case 1, if a pole is cancelled by a zero, or if a zero cancels a pole and the system function itself, then the system order is reduced by 1. That is important. Then second, case 2, pole of the system is suppressed by the zero at the input signal, or vice versa. The case 2 is where we are talking about the product of the system function and the Z transform of the system. So what happened? The pole of the system is suppressed by the zero in the input signal, or vice versa. Now when zero is located very near to the pole but not exactly the same location, the term in the response has very small amplitude. So when it is equal, it is cancelling, but when a pole is located very near to a zero, the corresponding term of the pole in the output of the system is having a very small magnitude, and the magnitude is dependent on how close the zero is located to the pole. Let us look at multiple order of poles and stability. How do they define? A necessary and sufficient condition for a causal LTI system to be BRBO stable is that all the poles lie inside the unit circle. This I have been very persistently telling this throughout, that the poles all must lie in the unit circle for a system to be LTI and also to be a BIBO. That means a causal LTI system is BIBO stable only if all the poles are lying inside the unit circle. That's a necessary and sufficient condition. In view of the fact that a bounded signal may have poles on the unit circle, it might appear that a stable system may also have poles on the unit circle. So, may also, we were talking about poles lying inside the circle, but due to the fact that a signal is already bounded, then the pole can exist on the unit circle also. So, that also can appear, the stable system may also have a pole on the circle. This is not the case if you look at this, since such a system produces an unbounded response when excited by an input signal that also has a pole at the same position on the unit circle. So, this is the case which we have to be careful.